All right, so this is lesson 5. We're building quadratic functions to describe situations. This is part 1. We'll do part 2 tomorrow. So, no, we did lesson 4 on Thursday.
Oh, practice problem 6.1.
Yeah.
Makes sense.
Unit 6. So notice and wonder, an interesting numerical pattern. Study the table. What do you notice and what do you wonder?
They're doubling.
What?
And then they go down.
So the x goes up by 1.
The y looks like it's... What's 16 times 3?
What's happening with our y? Okay, so for the y values, we said they're even. Are they increasing or decreasing? Are they all increasing by the same factor?
No.
They are not increasing by the same factor. What else was it you guys said?
Maybe it could be for like a power. Or like have a, whatever it's called up there, exponent.
An exponent.
But I don't know the e.
Okay. What else do you notice? What do you wonder here?
How it increases? How wide are they?
So is there a pattern?
I don't know. Are they
Yes,
multiples
they're
of eight?
kind of. So if you multiply 16 by 4, it's 64. But if you multiply 64 by 4, it's 256.
Okay, so you said 16 times 4
64.
is 64. What else? What'd you say after that?
And then if you multiply 64 by 4, it's 256.
Okay, so there might be something to that. What else? Do you wonder anything else about this? Okay, let's go to the next part. Falling from the sky. A rock is dropped from the top floor of a 500-foot tall building. A camera captures the distance the rock traveled in feet after each second.
That the fall became velocity causing the number of feet that it fell in amount of seconds to go up.
Okay, wait. Repeat that, but a little louder.
So when the rock falls, it has an increase in velocity, so it causes the number at which, like the speed at which it's falling to go faster, which means it will take less time to travel more feet.
So velocity increases as it goes down, right? Okay. So between 0 seconds and 1 second, how many feet are there?
16.
Okay. Between 1 second and 2 seconds.
A lot more than 16. Like 4 times that amount.
Actually, let's just leave it at, so we did,
There's 48 feet in between second 1 and 2.
okay, but let's leave it at whenever we have like a table. Are those the same numbers we had up there?
Yeah.
They are. How far will the rock have fallen after 6 seconds?
How tall is the thing?
How tall is the building?
500 feet.
500 feet tall.
5 feet in 6 seconds.
So it will fall 500 feet. How did you get that?
Well, because the ground hits there, and it looks like it's at its like max velocity at 4 seconds, so it'll fall the same distance as 4 seconds as it did at 5 seconds.
Okay. So if we were to subtract how many feet they were here, so 400 minus 256 is going to be, let's see here, it should be like 134, 144. So if there's only 100 feet left, it's definitely going to hit that in that next
144.
second, right? So our explanation for this would be that the rock fell 144 feet. Between 4 and 5 seconds.
I swear some math problems you don't even need math, you just need common sense.
So between, oops, I had an extra thing in there. 5 and 6 seconds. It would fall more than 144 feet. There is only 100 feet left. Until it hits the ground. All right, let's go to the next one. All right, page 2. Jada noted that the distances fallen are all multiples of 16. She wrote down 16 times 1 equals 16. 16 times 4 equals 64, 16 times 9 equals 144, and 16 times 16 equals 256. 16 times 25 is 400. She noted that 1, 4, 9, 16, and 25 are 1 squared, 2 squared, 3 squared, 4 squared, and 5 squared. Use Jada's observation to predict the distance fallen after 7 seconds. Assume the building is tall enough that the object dropped from the top of it will continue falling for at least 7 seconds. Show your reasoning. So, at 7 seconds, what would my equation be?
Can't you just do 7 squared?
Can't you just use signs and say that an object in motion will stay in motion unless stopped by an unstoppable force and then boom?
No, because that's not what it's asking.
But like,
No, this may have more to do with the gravitational pull.
it's still gonna fall. It's not just gonna stop falling. Because it's
But if
going
you
around.
have no gravity, it isn't going to fall nearly as fast. Or even at all.
Okay, so 16 times 7 squared, so for our 7 seconds, we'll square that. 16 times 49, because 7 squared is 49. 49 times 16 is 784, and we'll say feet. Okay, write an equation for the function with d representing the distance dropped after t seconds. So what could my equation be here?
It could be d times t squared.
Mm-mm.
Or not squared, to the second power.
Well, t will be squared, but it's not d times t.
Okay, so it'd be D.
What was consistent about all of the parts up there in our equation?
They were all multiples of 6.
Oh, so D equals 16 times T squared.
There you go. D equals 16 times t squared. All right, Galileo and gravity. Galileo, an Italian scientist, and other medieval scholars studied the motion of free-falling objects. The law they discovered can be expressed by the equation d equals 16 times t squared, which gives the distance fallen in feet d as a function of time t in seconds. An object is dropped from a height of 576 feet. How far does the object fall in 0.5 seconds? So what do I do here?
Plug in the
16 times 0.5.
It's times 0.5 squared. What's 0.5 times 0.5?
1. Wait, no.
What's 5 times 5? So 16 times 0.25. What's a quarter of 16.
3? No,
It is 4.
yeah. I was saying the 12.
3.
Depends on what you mean by quarter, because in time, a quarter's 15, because it makes no sense.
15 is a quarter of an hour. That's where that quarter comes from.
You really said it.
Let's go to the next page. All right, so to find out where the object is after the first few seconds after it was dropped, Alina and Diego created different tables. Here's Alina's table, and here's Diego's table. How are the two tables alike, and how are they different?
Alright, well. Is X the time and seconds guy?
Yeah,
Okay,
we could
so
say
X-
that's X or T.
Yeah,
So time and seconds, what about it?
they're both the same.
What's the same about them?
Or how they increase. How is it?
So time and seconds, just in general, the time and seconds is the same in both of those. And they also both have 0 through 4 and T. What else is alike?
Nothing.
They both describe the same falling object. Also, their distance is in feet. What's different here?
On Diego's, it's decreasing, and on Alina's, it's increasing.
Okay, so Diego's is decreasing from 576 feet. Alina's is increasing from 0 feet. What else is different? So for Diego's, we're going to say it's distance from the ground.
Oh, and the distance fallen.
Yeah. Okay, so Alina's is distance fallen. So they're recording the measurements from opposite ends. Now we're going to complete Alina's and Diego's tables and be prepared to explain your reasoning. So for Alina's table, we're increasing, and we have, what do you guys think our pattern is here?
I don't even know.
The same for one.
So it would be increasing by 4 for
Yeah.
the first one.
So it's 16 being multiplied by the square of our times, right? So 16 times 1 squared, 16 times 2 squared, right? Isn't that what we did earlier?
Yeah.
I think it's following the same pattern. Which I believe we had on our previous page back here. So it should be 144 and 256. Okay. What about Diego's table? What's happening here?
Oh, I'm down by 16.
So it went down by 16. So we went from,
576 to 560.
okay, what do we do here?
Minus 48. Did I count that wrong? Probably.
No, that's right.
I think you're right. So is there seemingly a pattern here? Okay, so if I put plus 16 and plus 48 on the other side, what do you notice now? What's happening?
Instead of adding them, it's subtracting.
Right. It's subtracting them from what? From the what?
From the distance.
From the max, like,
From the max. So from our 0 seconds. So from 576, we're subtracting 16 times 1 squared the first time. So 576 minus 16 times 1 squared. So for the next one, what did we do?
Would it be 560 minus 16 times 2 squared?
No, still starting from the 576.
Oh, okay, but then would it be the 16 times 2 squared?
Yes. So if we said 576 minus 64, does that give me 512?
Yeah.
Yes. So we're going to keep doing that. So 576 minus 16 times 3 squared. What's 16 times 3 squared? 144. So we'll take 576 minus 144 is, what is that? Don't use your calculator. You can do this.
What you asked?
What's 6 minus 2? Or sorry, 6 minus 4. I gave you the 2.
2.
What's 7 minus 4?
3.
And what's 5 minus 1?
4. You need a calculator for that, Ellie?
Okay, you're one to talk.
Okay. So, what are we going to do for 4 seconds?
576 minus 430. Wait a minute. 16 times 4 squared?
Okay. What's 16 times 4 squared? It's in the other table.
256.
Okay. What's 576 minus 256? What's 6 minus 6?
0, 320.
320. Okay. What's my formula going to be for t? What do we start with in every single one of these?
576 minus 16 times t squared. Yes.
Yes. All right, you will have practice problems to do on Canvas. Make sure you get those done. I believe I'm going to have them lock, I think Sunday, because next Friday is the last day that we can have anything done.